So hey guys, leaving off on last video, so let me scroll up here. We were talking about Newman's analysis. We went through that, and we determined the stability of when R is greater than half is stable. But now we're going to try a different method, which is Crank-Nicolson's. So, Crank. I'm just going to say Crank-Nicolson. We do the same thing here. We're going to start out with the final difference equations we have. So Tj of n plus 1. So at position j at a later time is equal to Tj at node j at a position of earlier time plus alpha delta t over position, and this is second derivative. But instead of just getting the positions at an earlier time, we're going to take the average of positions at an earlier time and the positions at a later time. So when we do this, we get T, J, N, so 1 minus 2 T, J, N plus T, J, so 1 of N. That's going to be the first part. You add this, so T, J plus 1. So now at a later time, that's 2 T, J, N plus 2 TJ. So I know that the later time to the left. And this is all going to be divided by 2. This whole thing. And what we can do is, let me get my draw. You can get rid of this 2 here. And we can put it here. And we can call this function here R. So as we move this down, you can get 2 Tj n plus 1 equal to Tj, and let's go and get this copy. So actually I can erase this part. Erase. And let's paste it here. And move it down. But instead now, you can erase this and replace this with R. And now there's no 2 here. We're going to say 1. So what this will do is it will no longer set constraints on a delta x and delta t values, which is good. So less factors to deal with. So we're going to move the Tj plus 1s, or the Tj n's and the Tj n plus 1s to different sides. And as we do this, we get okay. You get Tj n plus 1 R in front, 1 plus 2R. So you minus that. I believe it is still Tj minus. This should be plus 1 minus 1 n plus 1 is going to be equal to Tj plus 1 n R minus 1. So this is plus minus 2R minus RTJ minus 1 of n. I believe this is plus, your plus as well, your minus plus. So that gets the signs. And we can do now, oops, my bad, is Euler's equation from this. We can insert that in. So when we do that, we get TJ n plus 1 is equal to, let's see, I know it's going to be R E I K delta x, that's an I, minus 1 plus 2r minus RE negative I K delta x, and this is going to be sine, which is odd, cosine negative, so that's going to lead to some cancellations there, and do that to the other, so you get E I K delta x minus 1 minus 2r plus E I negative I K delta x. I made a mistake here. This would be T J n plus 1 times, it's equal to, it's still this, it's TJ n. And now we can simplify this. So this is where it says TJ n plus 1 is equal to, so what we did before, you can get cosine K delta x from those once they simplify out, minus 1 plus 2r, and on the bottom now we'll divide it. So yeah, we factored out the TJN up there, so we get, this is going to be different, it's going to be 1 minus 2r plus or minus cosine K delta x. And actually I forgot the r's, so that should just let me erase this. So I might have gotten some signs too wrong, but it should be 2r cosine K delta x plus 1 minus 2r. And then I think it's 1 minus plus 2r minus 2r cosine K delta x. So yeah, you need the r's in front of there. And let's see, we can factor out the 2r. So bring you down. Let's bring you down. Set that equal to. So I factor out a 2r from this. Get 1 minus 2r. 1 minus 2r cosine K delta x minus 1 on the top. From the bottom, you're going to get 1 plus 2r. This is going to be 1 minus cosine K delta x. And we can change a sign here. So for one of these things, so which one should I change, top or bottom? I want a 1 minus cosine delta x. So I'll have to change it up here. So we times this by negative 1. And when we do that, we're going to get plus, minus. That's the same. I want to think I want to do here. That's not that. This was already minus before. This was not minus, it was plus. This should be a minus up here. So we get 1 minus and 1. So we did that. So let me scroll down here. So we have this equation. We can simplify this now. We can say, hey, this is 1 minus 2r. You can say whatever's in here is a variable. So y over 1 plus 2r y. And what we can get from this is, oh, that's my bad. This is always going to be greater than 0. And as we scroll farther down, we could say r is going to be greater always than 0 from this statement, in which r is alpha delta t times 2, so different than the one way up top that we did earlier, delta x squared, so second derivative. And we can say this here is essentially 1 minus a over 1 plus a. And what you can tell from this expression, it is always going to be less than 1. So any stability that's less than 1, any value less than 1 for r is going to be completely stable. So that is what so any delta t, delta x constraints won't matter anymore. Know how big or how small they get. I mean, you could get an inaccurate reading, but it will not change the stability. The system will not be unstable by this anymore. So, system always stable by this. And that is what we wanted. So this is what the Crank-Nicolson values or method gives you. So we're going to have to code this eventually. The first thing is we're going to have, let's put the negative t, negative r, t, n plus 1, j plus 1, minus t, so 2, n plus 1, minus r, t, j, n plus 1, r, t, j, plus 1 n plus 1 minus 2r tj n plus r t j minus 1 n. So let's see, erase this. I forgot it's 1 plus 2r t j n plus 1. So this is what we're going to use as the function that we're going to do in the coding part. The problem is this one right here is a lot more complicated than this part right here, the earlier values, since they're somewhat going to depend, the later values are somewhat going to depend on the earlier values. And what we know is t is 0 equals 50. I guess t1 is equal to 80. So let's scroll down here. So let's say we have a bar that we did before. Blank, 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 blank. T is 0 and t of 1. So to wrap up this video, this is how I'm going to end it. In the next video, I'll be talking about how you use like matrices and what we're going to use in those for the code to get the final answer.